Cuando queráis.
Okay. Good morning, everybody. I'm Carlos Granell, the president of the Spanish National Committee of Large Dams. And I want to welcome everybody to this international webinar about modeling and digitalization on dams. This webinar, as you may know, is co-organized by the Young Professionals Forum of ICOLD and also the European Club of ICOLD and the Spanish National Committee of Large Dams. Here with us, you can see to Mateja Klun, the president of the Young Professional Forum of ICOLD, and also Alfredo Granados, the Secretary General of the European Club of ICOLD. As you may know also, this event coincides with the celebration of the World Dam Date initiative of the European Club of ICOLD, and about what my colleague Alfredo will speak after. Okay, the purpose of the event is to show the recent experience about digitalization and modeling to dam management and numerical modeling. Okay, and without further, I want to introduce Mateja Klun, president of the Young Professionals Forum, who will introduce the speakers and the presentations. Thank you very much to everyone.
Hello, good morning, good afternoon, good evening to everyone. So my name is Mateja Klun, and today I will be moderating the sessions. And let me start first by explaining some housekeeping rules. So as you can see, you are currently all muted, and you will stay muted during the presentation. But if you have any questions during the presentation, you can write them in chat. At the end of all the presentations, we'll have a 30 minutes discussion session where your questions will be answered. Also, if you want to ask a question during the Q&A session, you can ask moderator and he'll give you the permission to speak. Now, each of the technical presentations are 30 minutes long. And I will start right away by presenting the first speaker, who is Narjes Soltani. She is a postdoctoral researcher at the UPV Valencia, and she has an extensive experience in numerical analysis of large concrete arch dams. For example, she has analyzed into the details the cracking of the Karun 4 dam in Iran and did some amazing analysis of large dams in Spain. And Narjes, I would just like to invite you to show us your presentation.
Thank you very much, Mateja. Let me share my presentation. Vale. Thank you, Mateja, for the introduction. Today, I want to present a practical framework for dynamic analysis of dam foundation systems. The reason for that it comes from the challenge I had during my different projects. For every project, I had to search over tens of books, articles, bulletins, etc. So I decided to put every important parts I found together and prepare this practical framework that can be used as an accelerator to the dynamic numerical simulation of dam foundation system. First of all, we would have a review on some important basics. Then we talk about how we can prepare the dynamic inputs. Then we apply this dynamic input to the numerical model. And in the end, we talk about the interesting subject of damping. The first important thing is knowing different types of earthquake magnitude. In the literature, they may report the earthquake by different scale, like the Richter magnitude, shear, surface wave magnitude, body weight, and the most important one that as an engineer we normally use is the moment magnitude. Here in this graph, you can see the relationship between the moment magnitude with the other ones, and you can see that until the magnitude of 6, all the scales are almost the same, and after it they differ a bit. So if in one of the documents you, instead of the moment magnitude, you have another one with this graph, easily you can convert them together. The next step is knowing what is the design or analysis level. Normally we have two different level of analysis. First one, that is OBE, operating basic earthquake. We say that we are going to design our structure at somehow that we have just minor or acceptable damage, and the whole structure of the dam and all the rest parts, connected parts, should remain functional. But on the other side, we have SAE, safety evaluation earthquake, or MDE, maximum design earthquake. These two are exactly the same, just in different literature. They have different naming. We say that in this level, okay, we can accept more damage, but still in this level, we shouldn't have any uncontrolled release of water from the reservoir. So then for each return period, we should decide for each level of the analysis that we have here, we should decide about the return period of the earthquake. For choosing that, we can have two different approaches: deterministic approach or probabilistic approach. In the deterministic approach, which is the easiest one, we say I don't consider nothing. I want to design the whole structure for the maximum credible earthquake that can happen at site, and I design everything deterministically for that. But in the probabilistic approach, we also have two different parts. We can have standard-based or risk-based. In the standard-based, you can use a table like this that easily, this all have references, and the references are in the end of the presentation. You can use, in the probabilistic standard base, you can use this table that says that, for example, for the level of OBE, an earthquake with the return period of 475 years, or for the SEE, 10,000 year, would be a good estimation. But in the risk-based analysis, we don't choose a specific return period, but we consider a range of different return periods for the earthquake, and for each of them we calculate the conditional probability of the failure that comes from the uncertainties of the material, of the geometry, and etc., and the total probability of the failure can be calculated by multiplication of these two. Then what is a response spectrum? Response spectrum is defined for a specific earthquake record. The process of extracting response spectrum for a specific record is shown here. For the different structures, that all of them are single degree of freedom, and every of them have their own mass, stiffness, and damping, the motion equation can be solved for calculating the displacement, the velocity, and the acceleration, time histories, and also the period of each structure can be calculated easily by solving this eigenvalue problem. Then, after having the acceleration time histories, if we just keep the point with the maximum acceleration and we depict these points against their periods, we would have a graph that we call it response spectrum. So we keep this concept for continuing of the process. Another important thing is that in all these structures that we consider, normally it is accepted to consider the damping of all structure equally to 5%. And also, this process that I shown here can be done with lots of software like a seismo signal. The most challenging part is calculating the natural frequency of a dam foundation system, which is a multi-degree of freedom structure. For this reason, we have to calculate this free field motion equation that you can see in the right part of the equation. We have no earthquake, we don't have external dynamic loading, which means that the natural frequency of our system is independent of the dynamic load that we want to apply to our model. This equation can be simplified to this equation that you can see in this equation. We don't have any damping, so it means that the natural frequency of the system is also independent of the damping parameter. But now the challenge comes here. For a dam foundation structure, this matrix of stiffness and mass, how we want to calculate it. This is not like a building with the concentrated mass that we can calculate it easily. In some software like the Abacus, there is a button that you can choose and it will calculate you natural frequency automatically. But in some other softwares like Itaipu software, you don't have that option. So somehow you should examine how much is the natural frequency of your structure. Here, we want to show you how in any numerical software with the concept of resonance, you can examine the first mode natural frequency of the system. For this reason, we need to first build a numerical model of the dam foundation system with all the static load and all the static boundary conditions, and we sure that our structure is statically in equilibrium. Then we change the statical boundary condition to the dynamic one. Also, we change the static parameters, material parameters to the dynamic one. Then we want to apply different simple harmonic dynamic laws with different frequencies to the bottom of our model. Here you can see that I chose different same function, each one with the same, which all of them have the same amplitude but with the different frequencies. We apply one by one these loads to the dam, to the below the model, and we watch to see in which of these loads we have more response, more answers. So that load probably is the load that has the frequency close to the natural frequency of our model. Here you can see the example of a dam that in this point of the middle, we have the stress concentration. So I chose this point as a representative point. And if for this point, we draw the power spectrum of velocity of this point, you can see that when I apply the load with 1.5 hertz frequency, I have more response. So probably the first mode natural frequency of existence of this system is more close to 1.5 hertz. Then now we want to step by step prepare the dynamic inputs. First of all, we need for each return period know that what is the design response spectrum. Before we talked about the response spectrum, this is design response spectrum. That is a bit more complicated and needs a specialist for extracting that. Normally, this design response spectrum that from now on we call it just simply a DRS. DRS can be extracted from the national laws normally, or in the case of dam structures that are the infrastructures. Usually, a specific hazard investigation is done at the dam site, and they report you directly how much and how is the design response spectrum. Also, with every design response spectrum, they tell you, they report to you that this DRS is related to a branch of earthquake that have a specific characteristic. This characteristic can be accelerogram, magnitude, epicentral distance, hypocentral depth, soil shear wave velocity, and etc. So now our objective is to find earthquakes that are similar that have characteristics similar to our design response spectrum. And FEMA 65 says that for each return period, we at least need 3 different records of the earthquake. For finding the earthquake that have the same characteristics as the design response spectrum, we can use the online library of PEER, which is a very useful tool that here you can add your characteristic and you can download every lots of different earthquake that you need. Here, in this step, we download lots of different records. Then later, we choose just 3 best one and delete the rest. I also here prepared a list of famous earthquakes that mainly are referenced in the literature. You can see here the characteristic. So if your return period has characteristic close to this earthquake, as they are so important in the literature, I recommend you firmly that include this record also to your analysis. So now we downloaded lots of different earthquakes and we want to do the scaling process to match this earthquake to the design response spectrum that we have. The process is shown here. First of all, for each record, we extract the response spectrum of the acceleration by the same process I explained you in the basics. And then with having this and also the design response spectrum, we fill this table that we have different periods. For each period, we have response spectrum, we have design response spectrum. Then we calculate the ratio of DRS to RS. Then for the range of 0.2 to 2 times of the first mode period of the structure, we can calculate the mean of the ratios. This mean of the ratios is the scale we need for doing the scaling. Also, we can calculate the mean square error. That is important for choosing which earthquake is better than the other one. So with this scale factor, we do the scaling. We do the scaling of response spectrum. Now that we see it is fine and we like it, then we convert back the response spectrum again to the acceleration time history and we keep this. All this process I explained you also can be done automatically by the PEER Align website. You can just choose the scaling method and you can upload your design response spectrum and it gives you all the earthquake that you need with the scale factor and the error. So then from here, if you sort the error, you can choose the 3 records that have the least error and choose them as the best one that have more match to your design response spectrum. Another important thing is that if you are doing a 3-dimensional analysis, you need both horizontal direction of the record. So we recommend you that first of all, with the SRSS calculation, you can combine these 2 horizontal records to 1 record and then scale this record and then use the same scaling factor for each of them separately. Also, if you have to apply the vertical component also to your model, and if there is no special hazard study for the vertical component, you can also use the same scale factor of the horizontal scale factor for also the vertical component. But we saw in this simple scaling method, we can choose our desired record. But the thing is that, as you can see, that sometimes this simple way of scaling cannot give us a beautiful match. As you can see here, we don't have any acceptable match. So we recommend you, after doing the primary scaling and choosing your 3 best records, you finish the scaling, but also another advanced scaling method. Here we propose you the Abrahamson method that you can see here. This green nuts are the scale by the Abrahamson method, and the red one is the design response spectrum that you can see we have a perfect match here. So first doing a primary scaling, choosing our 3 best one based on the error, and then complement it with the advanced method of the Abrahamson. This method of the Abrahamson is supported by some software like Seismo Match. Then now we scale our record. We may need to do some modification on our record. The modification that we may need are the convolution analysis, baseline correction, and filter. What is the convolution analysis? That, as we know, the records that we downloaded are the motion registered by the accelegraph, which normally is installed on the bedrock close to the earthquake site, close to the earthquake zone. Then with scaling, we move this motion to the site of our project, to the site of the dam. Now, then we have a numerical model that we are choosing a zone of the area, a zone for doing the numerical analysis, and then we want to apply the load, the dynamic load, to the bottom of the model. But the thing is that this scaled record that is for the surface record that is at the place of our dam, if we put the same records to the below the foundation, this way, while it's coming up to the dam side, it propagates and increase, and when it comes up, it's not. It is not at all the same desired record that we wanted. This happens when you are adding. This happens when you have two situations. One of them, you are putting the earthquake below your foundation, and second of all, you are simulating your foundation with mass. If you have this situation, you cannot put the same scaled record below your foundation. You should do the convolution analysis that says that which motion should I put below the foundation, to be sure when it comes up and reach to the dam location, it is my desired scaled motion. What is the baseline correction? A baseline correction comes from an error that happens during the scaling. When we do the scaling on the records, we change the parameters, the characteristic of the earthquake a bit. One of the things that changes is we change also the history of the velocity, and we change the area below the velocity that is the displacement. So sometimes during the scaling, we see that the last point of the displacement of the record is not 0. It means that we have the earthquake is done, but it still is like we have a residual displacement in our model. For making this displacement against 0, we can use the baseline correction that in this method, they come and add a low frequency velocity wave to the first velocity in a somehow that be sure that the final displacement is 0. And what is filtering? You know that when we are doing the numerical simulation, we have to do mesh in our model. But the largest allowable size of the mesh that we can have in our model for doing a dynamic analysis can be calculated by this formula, that F is the maximum frequency of the records. So if we are applying a record of the earthquake to our model that has lots of high frequencies, it may end to extremely fine mesh requirement. But sometimes these high frequencies that you can see here, they don't affect much your results. So you can easily cut them and remove them from the model. You can have a you can have bigger mesh, and everything would be better. So this process of cutting high frequencies of the record is called filtering. Here, we want to present you the software of IDATA that we developed in the IPRESA's risk analysis company. IDATA is a short of the IPRESA's deconvolution analysis of target acceleration. With this software that we developed in IPRESA's, you can easily do the deconvolution analysis, the baseline correction, and also the filtering. The part of the code of the deconvolution analysis in this software is based on the famous code of Shake 91, which is a code developed by the Berkeley University. Here you can see the first window of the software. You can define the column of different material in your model, define the and you also need to define your target acceleration with all the material you need, and also you need to define these two curves which are changing the damping and the shear modulus against the Étore. With putting all this, you can here tick the baseline correction and also filtering at any cutoff that you like. And it gives you all the results of the deconvolution, filtering, and baseline correction. It's a very simple and useful and special interface for doing these jobs. Now we have our records. We scaled it, we modified it, and they are now ready for applying to our numerical model. But the important thing is that when you have the viscous boundary condition, never ever apply a history of the velocity or history of the acceleration to the same boundary that you have viscous condition, because viscous condition and the velocity and acceleration, they are from the same family. So if you add one of them, another one automatically would be removed, vanished from your model. So if you are working with a software that forces you to just work with the velocity and acceleration, like Itasca softwares, you have to transfer the velocity with this simple formula to the Étores, and then instead of applying the time history of the velocity, you can apply the time history of the Étores to the bottom of your model. And the last part, but not the least part, is about the damping. As we know, we have two famous types of damping. We have Rayleigh damping and we have historic damping. Rayleigh damping, as we know, we can use it for elastic structures or in the structures that the level of the plasticity is allowed. In this model, the damping would be defined by two parts of the mass proportional damping and also the stiffness proportional damping. But in the other side, historic damping is used for the models that we have considerable plastic flow, like this, the one that happened in embankment. The most important thing is that never ever use full definition of Rayleigh damping and historic damping at the same time to your model, which is too much for the model. For the Rayleigh damping, we may need to define these two coefficients of alpha and beta to our model. And this alpha beta can be calculated by these two different formulas. In the first one, we need two frequencies of the two modes of the motion of our structure, that these two frequencies can be calculated by the same strategy of resonance that we were talking before. The first most answer can be the first mode and the second one can be the second mode. Also, we need the critical damping ratio, that for the concrete dams, normally it is accepted to consider is 5%. Other side, in this formula, we need the first mode natural frequency that we talk about it, and then we need the minimum critical damping ratio, that if you do the convolution analysis by the IDETA software, one of the results that in the end gives you is also the damping parameters, this minimum critical damping for every layers of your model separately. And for the historic damping, we need to define this curve to our model, which is the change of the degradation of the shear modulus against the strain. Most important things. Never think that this is supplement to any nonlinear model of your material. This is just a curve for hysteric damping, and the definition of the nonlinearity of your material behavior should be done separately in the other section, other part of the definition. Another important things that happens when you are using the hysteric damping is that here in the first of the analysis, in the first of the graph, you can see we have a horizontal line, which means that when the level of the strain is low, you don't have any degradation in your stiffness. It means that you are applying no hysteric damping to your model. So for the beginning of the model, it is recommended that you can use a small amount of Rayleigh damping, can be 0.2%, but applying this amount of Rayleigh damping just proportional to the stiffness part, because in the first of beginning of the analysis, the stiffness is maximum, Rayleigh damping would work, and when the strain increase, the stiffness decrease, and this part of the Rayleigh that is just proportional to the stiffness would be removed automatically, and in the other side, hysteric damping would work. So in this way, you are sure that these two dampings are not working at the same time together, but they are completing each other. Here I have some important references. Thank you everybody for listening me. Thank you Mateja and also the SPANCOLD for giving me this opportunity. I want also thank especially for my supervisor, Professor Ignacio Escudero Bueno, which have been supporting me all the time, and I learned lots from him. I also want to thank my former supervisor, Professor Mohamed Tari Ahmadi, which have been my supervisor for more than 7 years for my master and my PhD. I think he's also connected today here and he is with us. I want to tell him thank you for all the lessons you gave me, and now I am using line by line of every note you gave me. Thank you very much, everybody.
Thank you, Narjes, for your very structured presentation and step-by-step explanation on how to perform numerical simulations of large concrete dams. For now, I will ask you if you can stay here until the Q&A sessions. I bet there will be questions directed to you. And for us, let's continue. The next presentation is then monitoring and surveillance at Itaipu Dam, which will be presented by Funchal de Faria, PhD, who is a senior engineer at Itaipu hydroelectric plant in the areas of dam safety and at Concrete and Materials Laboratory. He's also a member of the Brazilian National Committee on Dams. So hello to Brasilia. Good morning.
Yes.
And also a member of RILM, ICOLD, and ATSO. He has more than 20 years of experience in the field. And please, the floor is yours.
Good morning. Thank you very much. Can you hear me? Can you see my screen?
Yes, we can hear you. We can see your screen.
Thank you very much. It's a pleasure to participate of this webinar, and thank you very much. I will show you some aspects of monitoring and surveillance at the Itaipu Dam. We have only 30 minutes, so we have lots of work that I could not show you today. Yeah, but I'm here to show you if you want more information. Sorry. Itaipu Dam is a large dam, and we have almost 8 kilometers length. These are the parts of the dam. So from the right to the left, we have an earth dam, the spillway, a buttress dam, we call right wing dam, and we have 6 blocks of buttress dam and the right connection blocks. And after the main dam is a hollow gravity dam, and we have hollow on the joint and the core of the block. After we have the diversion structure is a gravity dam. And after the connection, the right connection, the left connection blocks of buttress dams, is a buttress dam. And then we have the rockfill dam, and finally the earth dam of the left part, left stretch. Our beliefs relies on 3 points, and that we don't have absolutely safety conditions. This does not exist. We have a feeling of it depends on who is feeling the safety. We don't have, and we don't have, and we must not do it alone. So to avoid decisions by only one person, only one technician, or only one engineer or technician, and there's no coincidence. So the instrumentation in Itaipu, we have some key blocks. These black ones are key blocks, fully instrumented. We have blocks with few instruments and blocks without instruments. The key blocks have a full of instruments, several instruments. We can see the list in the right part of the screen. And the main block, this one is the main block of the dam, the highest one. We have on the foundation shear key, because of a feature, a geological feature, is the joint A to block the displacement between layers of the compacted rock. Okay. The instruments by the instrumentation, we have nowadays over 6 million measurements in 40 years of monitoring the dam. the registered readings are allowed to any of kind of analysis, and numerical and numerical and engineering analysis. Nowadays, we have 8,000, more than 8,000 instruments installed in the dam. From this, we have 5,500 drains, 4,500 are of foundation, and 100 in the concrete, some on the head of the blocks, and some on the joints. The equipments are constantly benchmarking and calibration. The equipment has constant maintenance, and we make replacement when we need, when they are not working so well. In 2022, but 2023 was the same. We had 150,000 measurements, and we had less than 0.75% of we call revision field revision. That is when the technician needs to go back to the field to make a new reading of in the instrument that shows an abnormal reading. And we have 2 planning altimetrics campaign by year. We are now using the TM60 of Leica to make these campaigns. By the instrumentation, we measure deformation and overturning. Now, so something like this, the deformation or the overturning. We are using pendulums, and in the past we used the coordinometer. Is a device made by Lenec in Portugal, and nowadays we are using the micrometer. Is a system developed by our technicians to measure the displacement and between the wire and the structure. We use rod extensometers to measure the deformation of foundation, mainly of the foundation. So like here we have some samples of the displacement, and the most part of them are automated by geocon devices. The uplift and drainage is measured by piezometers and water level indicator. So we can analyze the piezometers, and by this analysis, we do assays for testing the operationality of the piezometers. So we can show you a result of this assay, of one assay we made. We are using a sensor. We put it inside the piezometer, and we fill with water, taking care to avoid the break of the instrument. We have, I said we have 5,500 drains. Okay, we clean it each 4 years. The blocks, we have concrete drains are this way, in the joints and in the head of the block. We are now using the boroscope. Sorry. We are now using the boroscope to see inside of the drains and the piezometers. And these pictures show you one of the inspection we made by this boroscope, and we could have some information of in which layer the water is going through inside the drain. For displacement, we used for almost 40 years the longometer. The device is a little bit difficult to use because it needs the strength of the technician, and each technician has a different strength to put the device on the pins, so it could give us some differences on the readings, reading results. And nowadays we are using the triorthogonal joint meter. So this device is too much is not so heavy as the other device, and the precision is better than that one. And the displacement displacement of the block over the foundation, we are using inverted pendulums. The geodesy, as I said, we are using TM60 for campaigns. We have 8 piles outside the dam and some points to measure in the dam. And the altimetry, the vertical displacement, is measured by this device of Leica, also the Leica, to measure. And the data analysis, we think in four points: the reliability of the readings, and so the technical staff is ready to make these measurements. So the variability of measurements is very small, almost zero. We do operationality tests and validating of the measurements using more than one instrument to comparing instrumentations, different instruments, to guarantee this operationality. After the readings, we make validation. So we use old data for statistical analysis, and then we validate new readings by this analysis. We make treatment and analysis of the data by models of cause and effect. We analyze nowadays the trends, so we see we make some visual analysis in the graphs, and then if it needs, we do the numerical analysis. And nowadays we are using some statistical tests as KP, SS, and ADF to check the trends of the historical data. And we are working on forecasting models to ensure that the readings are reliable and they do not need any revision in field. We take care of some concerns, so we could make some readings with the technicians at the same time to compare if the readings they make could be considered the same. So you can see on these points that when we are registered 14 readings at the same time, so we could not see any difference. So any technician has the same capacity of reading, and this graph shows you the result of the reading of the made by the technicians against the automated readings, and we can see that the readings are the same, almost the same. We take care of operationality of the instruments. So this is a sample when we had the one rod extensometer blocked by powder. The displacement was not correct, and we saw this one and we made the maintenance, and the instrument turned to work correctly. Nowadays we are thinking in having new kinds of limits of alerts for the working of the instruments to show us when the instrument behaviors like this. Another concern is about the trends. So the instrument shows the trends by a graph, but we need to see the scale of the graph, and to ensure that in 40 years we had 0.5 millimeters of trend. So what is this trend in terms of the stability of the dam? So we need to take care of this. About the forecast, and we use, as I said, some models using sines, cosines, and for the temperature behavior, and another kinds of causes, and to see the effects on the measurements of the instruments. And we can see here, we can see that when the level of the lake went down, the instruments, this piezometer showed the behavior, showed the behavior by this cause of the this connection of the instrument with the lake. We make the maintenance of the instrumentation, and we maintain it clean and working to avoid any kind of trouble or problem in the results of the measurements. So you can see some pictures of this work. In the visual inspections, we have some rules based on the several experiences of the companies around the world. We divide the inspections in regular and informal. We make the planning every day, and we have an event library to avoid technicians to write different names of the same event. We call event instead of anomaly. And the events are encoded, and they have an address by coordinates X, Y, and H. So everyone can go to the same to see that event that recorded and find it. And we put in our database the length or the stations or the areas of the event. Depends on which event we are treating. We make the classification of the event by magnitude and hazard level. So this allows the engineers to make decisions on which one we should start to work on. I bring some pictures of the visual inspections. This is an upstream inspection we made. So here is the unfolding connection. To the left we have the Rockfield Dam, and this one is a buttress dam. The left connection dam. These are the piers of the spillway by an upstream inspection. This one is a downstream inspection made when the river level was very down. And this one is the slope after the ski jump. This is the ski jump of the left ski jump of the left chute. This is the central chute, and we make the inspections by boat and walking through this parts of the slope. This one is inside of the powerhouse, the level of machine covers. Another pictures. We have other pictures about the spillway inspection now on the chute. So we could see some things that are of the structure, some features of the structure, and some materials found on the slab. This one is the buttress dam and hollow gravity dam pictures. Another work we do in the Itaipu is to control the crack on the concrete structures. In the past we used the scaffold to make this one by Mitsutoyo devices, and recently we tried to use high resolution pictures to make this analysis, but we had so many small cracks and dirty that complicated our analysis, so we decided to not use it anymore. It's too expensive to use. We make the mapping of the seepage in foundation between the blocks of the buttress to see the seepage in the fractures of the rock, so we can analyze the flow by the foundation. And we are now employing technologies nowadays to improve our analysis. So this one are pictures of the multibeam used in the surveillance we make. So you can see that we have almost the same feature of when we were constructing Itaipu. We are using the mobile mapping equipment to make 3D images for use in beam analysis. We are using modeling and analysis by software to ensure that the analysis to easy the analysis of the stability of the dam. We are using our laboratory to make some special studies. These studies are of mortar to repair the chutes, the slab of the chutes. So we are studying this and applying, and when the chute, the gates are open, the flow of the water can help us to understand how good is our repair. We have a MAV that we are using to analyze the substract of the old concrete. We analyze the water flowing by drains to ensure that the substances will not cause any problem to the dam. Some another tests in laboratory we do. I will not use not spend some time in this information. Another important thing we do is the knowledge management. We consider that managing is an important Itaipu asset. The knowledge based on experience of the engineers accumulated over time is important to show to the newer engineers. We developed a system for initial training and periodic recycling of the members, the technicians, so they can access every time they want, anytime they want to see and to remember. And this combines the explanatory videos and assessment exercises, so they could train by themselves. We have a known team of engineers and technicians. They are crowded in the dam area, aiming to act quickly in the emergency situations. As I said, we have the knowledge management. The current team received knowledge from engineers and technicians who participated in the design and the construction of the plant. And nowadays, we have a few of these members of the design in the construction, of course. Our staff participates in association external committees like ABRAJ and CBDB are Brazilian institutions, and ICOLD, ASDSO, and RILEM are international commissions. We are constant training the team by courses and the participation in events. So you can see some pictures of them working in field. And each 4 years, we have a meeting with an international board of civil consultants. They are specialists who participate in the design and construction phase of Itaipu. They have international experience, of course, and the knowledge in hydraulics, hydrology, geotechnics, and concrete. This, as I said, this occurs in each 4 years, and the last one in November 2022. And I thank you very much for the patience and the attention. Thank you.
Thank you, Étore, for your presentation. Also you, I'm asking you if you can stay with us until the Q&A session at the end. And now I am inviting the next two speakers, Stefan Hoppe and Rubén Sancho, who will talk about digital tools and solutions for dam and reservoir management. So Rubén Sancho has a PhD in civil engineering, and he is a member of the technical committee on monitoring at SPANCOLD. He is also a manager of the company Altius and technical director of INGENIERÍA. He has more than 15 years of experience in the hydraulic and geotechnical work sector. And Stefan Hoppe, he has a master's degree in civil engineering and international master's degree as BIM manager. He is also a member of the technical committee on dams and valleys of SPANCOLD, and he works more than 20 years in the field of dam safety and surveillance. So I'm handing the microphone to you two.
Okay, thank you very much. Can you hear me and see my screen?
Yes, we can hear you. We can see the screen.
Great. Okay, so we divided our presentation in two parts. I will start, and then Rubén will talk about more details in the last 15 minutes of our slot. So, good morning, good afternoon, everybody. The word digitalization is something that we hear everywhere and every time, actually every day. And it's supposed to make our lives easier and better. But is it really like this? So that's why I would like to show a little bit what does it mean for our dams and how can we benefit from it. First of all, I will give some basic ideas about digitalization and BIM, and then present some different solutions like digital glasses, dam safety management platforms, and 360 images. And later, Rubén will enter also in more detail with other solutions. Digitalization is about optimizing processes and organizing data. So there are a lot of tools on the market that help us to bring the information together, to make it easier to make decisions. So it's very helpful on the first point of view. On the other hand, it's not only organizing existing information, but we also get more information. There are scanners, different sensors that have more geometric information. We have to handle them as well. And now there are also drones flying around our dams, taking photos, making videos. And somehow we have to handle all this information. Digitalization in the construction industry is a bit special because it's not linked to an abstract project, but to a physical infrastructure. And this helps us to make a visual organization of the data based on a model, a 2D or 3D model. So in this way, we can combine our model with, or the data model with a geometric model, and then add additional information. So then we don't have only a 3D model, can be 4D, 5D, depends on the information that we include, the schedule, the costs, facility management, health and safety. But finally for us, it's also dam safety or dam safety management. An important aspect about this data management is not to have it isolated. It should be integrated in different dam safety tasks. Here I show you a scheme from the ICOLD bulletin on surveillance. It's already a couple of years old, from 2008, but where we can already see how dam safety management is connected with other tasks like surveillance, safety reviews, and maintenance works. And then it helps also to connect between the different work processes. What else is important for information management? Actually, there I learned quite a lot from my children, because we create a lot of data now also with the drones and other sensors, but we have to select the best of it and then organize this data. And when it's organized, then we can do something with it. And this should not only be beautiful, it should also be useful in order to help us. Another aspect is sharing information. This is something my children don't like so much. I guess you always like to share the information that you get with other people and the collaboration. There are different platforms that help us to centralize the information and share it with different experts like geotechnical specialists, monitoring technicians, surveyors, dam safety engineers, also with external consultants, and maybe also the authority. And it's not only about sharing information, also feeding the platform with new additional information. And in this way, we can bring the dam site and the office together, because on the dam site, we get the information, but in the office, we make the decisions that in the end have to be implemented on the dam. When we go over to the tools, quite interesting solution for improving the communication are these, let's call them digital glasses. They are maybe a bit like a mobile phone. They have a small display, have a camera, and with them you can make a teleconference and talk with experts in the that are in the office. So in this way, on the dam, you achieve remote assistance for visual inspections or, for example, operation and maintenance works. And this is especially interesting when you need immediate solutions and you don't have the time to travel, or if it's not possible to travel, for example, in pandemic situations, or if simply you just don't have, there's not the budget for traveling costs. Also for training, it is good. And if you compare it with a video call with a mobile phone, the good thing about these glasses is you've got two hands free. That means you can move around freely and safely around the dam. You can hold the handrail, write something down, and do certain works. And at the same time, you get help from external experts. Regarding the model, it's not so easy as in the Wild West when you say this is the good one and this is the bad model. It always depends what it is needed for. And quite often, even the ugly one might be the best solution. So it depends on if you want to make a public presentation, if you want training, if you want a model for operation and maintenance or analysis of monitoring data, or structural calculation, you need different kinds of models and should always define the model in the way how you need it. The BIM solutions give us the opportunity that we combine the geometry with additional information by adding different parameters. For example, here with spillway gate, we can include photos, dimension, information about the manufacturer or operation works that have to be done. Or here we can see a pendulum with calibration values and other information that is needed in order to work with this monitoring device. The next step would be to link more data to the model, like we did it here in this example, in this online dam information system, where we link monitoring data, visual inspections, and different field procedures. In the upper part, we can see the model of the dam, which can be moved freely. And below is the database with different functions and configurations. When we have a look at the lower part, for example, there is a list of the monitoring data, also some charts in order to visualize it in a better way. We can choose, for example, the sensors that have triggered or exceeded a threshold value, and then synchronize it with the model and directly find the sensors that have been chosen. We can get closer to them and also make comparisons to see if there's some other sensors that might give us a clue about what or why this threshold value has been triggered, and see if it's in other sensors it is the same. As we have a model, we are not just depend on some 2D drawings. We can move the model and get a better impression about the location of the sensors and the dimensions. Another kind of information that we included is some forms from field work, like the sensor status, visual inspections, or photo documentation and incidents. And the idea is on the field to fill in these forms on mobile devices, and then they are directly synchronized with the database and immediately available. And the idea is not just to manage afterwards the forms, but the information that is inside these forms. For example, here we have a breakdown of different maintenance incidents, and below a breakdown of the visual inspections. And there we can, for example, select the incidents that are in progress. We have also information about if they are related to a certain block or a gallery. And we can also synchronize it with the model and see directly where these maintenance works have to be done. Or we do it in the other way. We choose an area on the dam and then see if there are some pending maintenance works. Other information that we included are observations from visual inspections. We have a list of different incidents or observations, and then we can choose, for example, I want to have a look for the C page. I get close to it, see there's a mark where it has been observed, and then I can get access directly to photos or additional documentation. So here we can see on the downstream side where this C page on the dam has been seen. And now this is the interesting part of bringing information together, because now in the same database, we have our monitoring data, but also results from the visual inspections. And in this way, we can bring this together and get better conclusions. Of course, it can also be seen as a document manager to include 2D drawings or photos. And this helps us to assign photos to different areas of the dam and find them very quickly. Another field of application for models is the virtual reality. These are maybe models that have less information but are nicer, and they are quite good for public communication or for internal meetings. and the visualization of information, also for training. So you can make a virtual visit on your computer, or even with three-dimensional, with virtual reality glasses. The preparation of models can take quite a lot of time and is more cost effective. So maybe a different alternative are the 360 images. There it is possible just in a few days prepare a model with site visit by using special cameras. It's even possible to make it with mobile phones. In this way, you can also make another kind of virtual visit of the dam. These models include obviously different kinds of information, but it's also possible to add more information. Like here in this example, we've got piezometers, and this information can easily be added. And if you repeat this kind of visits, so it's possible to compare, for example, every year or every 5 years, these photos with each other. It's also possible to add hyperlinks with more information, and even measure inside these models to get also geometric information. So before Rubén starts, I just give some first conclusions. So data and information must be managed efficiently, and by applying new technology, we can make them really useful. But it's not always the most expensive or the nicest solution, which is the best. So always focus on what it is needed for. And it's not only about technology, it's also about the people and processes. So it's important to involve everybody who has to use the software or the solution, so that it is really working properly. And in this way, we increase the knowledge about our dams, can improve the decision-making, working procedures, save costs, and finally also improve the safety of our dams. So thank you very much. And then I would like to pass the word to Rubén.
You can see my screen, right?
We can hear you, but we don't see your screen yet. Now we can also see your screen. Yes.
Okay, good morning and good afternoon. Thank you, Mateja, and thank you to SPANCOLD for allowing me to be in this webinar. It's a pleasure for me. We are going to start with the index, which is divided into 6 main sections. The first one is data collection and types of devices. In second place, we are talking about device selection, and then about 3D modeling. We'll continue with an application of 3D models for monitoring. Then we'll see some cases studies, and we'll end with the conclusions. We can classify data collection depending on the type of device to be used, ground, aerial, or aquatic. About ground devices, there are heavy and light devices. Some light devices doesn't need parking, and we can do the capture data by walking, like we can see in this picture. The quality of the point cloud is not like a static device, but it can be appropriate on certain occasions. In our experience, although the manufacturer says that they are appropriate for galleries, they are not adequate for indoor use because lose signal easily and doesn't allow post-processing. Within the light device, there are static ones. This device must be static during the capture, like in this image. The light device are on the tripod. In addition, some models allow the capture of 360 images and LiDAR data. This is a LiDAR data picture, which allows to have an interesting virtual tour like we have seen before with Stefan. If we need a high performance, there are heavy devices. It's important says that this high performance is according to the technical sheet. These devices are more difficult to handle, and especially to correct location. Therefore, they are suitable for flat environments, but not for large structures or structures with difficult accesses. Dams, for example, are located in riverbeds, ravines, etc. Therefore, have a complex positioning and not homogeneous point clouds with parts of the dam with different density and noise, and for sure, shallow areas, because it's difficult to have visual of all area of the dam from the ground. In the second section, we'll talk more about that. Besides, we need a great deal of time to capture, and therefore a high cost. On the other hand, there are aerial devices. In the case of nonlinear structures, like dams, which have a big vertical component, captured by multi-rotor drones is appropriate. This allows covering and therefore data collection from any location. If we have vegetation, for example in access roads, with the last generation of LiDAR drones, the filtering is automatic, and therefore the 3D model is easy to make. We can see here, we can see the ground perfectly under the vegetation. This is before the filtering, and this is after the filtering. Finally, in data collection, we talk about aquatic devices. They are monobeam and multibeam echo sounder. The monobeam captures one line with real data. That is, we only have real data in a line under the consender. For example, in this picture, we only have real data in these lines. And therefore, we have a digital terrain model by interpolation. However, with a multibeam, we can capture areas with real data. All this area is captured with the consonder. Therefore, we don't have to interpolate. For example, in this case, here we have a dam, and if we take a cross-section, we can see the 3D point cloud and the cross-section. This is the dam facing, and this is the suction cone of the bottom outlet. Before starting data collection, it's important to know the structure that will be digitalized, and therefore the methodology for get a high quality point cloud. Usually, prescriptions are according to the technical sheets, but it's not the fundamental aspect. The most important are the boundary conditions. In dams, there are discharge channel, intakes, spillways, and more different elements. Then, choose the device should be taken into account all these conditionals. With a drone, we don't need parking spaces. However, with a ground device, we'll have a lot of positioning and will be far from the dam. Regarding to the object device distance, an object device incidence angle from the device to dam is always maintained with a drone, and therefore we'll have a device adapted to our structure and homogeneous point cloud. That implies real and precise geometry. However, with a ground device, the distance and the incidence angle are different. For example, in this case, we can position in our device, maybe here, maybe in this other row, or in this. But for sure, it's impossible to position it in all this area or in this area. And inside the channel, maybe it's possible, but for sure, very dangerous. That implies that we'll have an heterogeneous point cloud and shadow areas. Now, we can go to modeling from the real point cloud and extract easily necessary sections. For example, here we can extract a section from the spillway. And then we can check and review elevation in absolute coordinates. Also, we can see the elevation from an area in a range of colors. For example, we can see it on a spillway lip. It allows us to know where it will start to pour. This red area is higher than this yellow area. Then it will start to pour through the yellow area. It's important to note that either with photogrammetry or LiDAR, we'll have an homogeneous and georeference outdoor point cloud. We can import the point cloud into the design software and start to draw the 3D model. Finally, if we have taken photos of the structure, we can give texture to the model. Okay, now we are going to see that once a structure or terrain is digitalized, we can control their movements or variations. Then, if we have a point cloud of a structure of 2 different times, this is the upper part of the dam, we can compare it and show their difference. This case is the upper part of the dam, and we have the movements value of the arch of this arch gravity dam. Here we have a rock massive case. If we compare 2 point clouds of different times, we'll have their movements. But the most interesting thing about this methodology is that we can see 3D variations and interpret it. In this case, we have here high values of movements, near to 45 centimeters. And there are null values. This means that there is a crack and a possible detachment of this part. If we go to the 3D model, we can see the crack. We can apply this methodology to small and large surfaces. In my opinion, the next case is an interesting example of things that we can do from a digitalized dam. From the aerial point cloud that we can see in this image, we can make the digital terrain model. And then we simulate the excavation of the foundation from as-built maps. This is the foundation simulated. Besides, we simulate visible surface drain layers of the foundation. From the geological map and knowing deep and deep direction, we simulate the drain layers. This is the drain layer simulated on the foundation. Therefore, we can choose the best places of draining to drain the foundation. In the 3D model, we can see the best places to drain. In this other case, with the aerial outdoor point cloud, this is the aerial outdoor point cloud, and gallery indoor point cloud. The scan of the gallery was made with a light device and captured with LiDAR and 360 images. This is the LiDAR and this is the 360 image. If both point clouds are georeferenced and in the same coordinate system, we can overlay. Here are overlay both point clouds. Here, in this case, we want to know if the gallery was under the spillway. We can check it in this model. And in that case, we want to know the distance between them. We got it from this section in the 3D model. As we've seen before with Stefan, we can make a big model. The last case we are going to see integrates an aerial point cloud. This is the aerial point cloud, and a bathymetric with a monobeam echosondil point cloud. Is this? And we integrate a testification of a geological survey. With this model, we can extract real sections. This is the section that we extract from the model. And the necessary anchors to improve the safety coefficient of the dam could be defined without reaching the reservoir. We can see in the cross section this distance between the anchors are in blue, and the reservoir. This is our safety distance. Also, in this area is this model. We can extract from the 3D model the minimum length. This is the minimum length that we need to anchor it to the foundation. To finish, we'll see very quickly the main conclusions. When choosing the device, it's not only the characteristic of the manufacturer's technical datasheet that must be assessed. We must know what we need and the purpose, and based on this, choose the device that best suits its boundary conditions. Outdoors, the choice of data collection with drones is usually the most appropriate. Indoors, drones are beginning to be marketed, but nowadays, the use of terrestrial device is more appropriate. The integration of point cloud of each element is simple. And from the point cloud, we can easily extract sections and digitalize our structure in 3D. Finally, the comparison of 2 point clouds provides us with the variation between both. That's all, and thank you very much.
Thank you, Stefan and Ruben. Also, both of you, I'm kindly asking if you can stay until the end so you can participate in the Q&A. And now it's the time for our last presentation. The title of the presentation is Understanding Accuracy, Uncertainty, and Automation Opportunities for Spillway CFD Modeling, the GARRISON Dam Case Study. The presenter is Jonathan Bouchard, and I guess we are now again going on the other side of the Atlantic, so good morning to you, who is a CFD engineer at Flow 3D Hydro and has a vast experience in modeling software development in the field. And we are very looking forward to your presentation. So please.
All right. Can you hear me well?
Yes, we can hear you. We can see your presentation.
Perfect. Well, good morning or good afternoon, wherever you are. So yeah, welcome. Today I'll be taking you to the world of computational fluid dynamics simulations, presenting you some of the work we have done on the GARRISON Dam. This was prepared actually for a workshop on this dam for the US Army Corps of Engineers a little bit more than 1 year ago. And we took this as a case study to explore the kind of accuracy, uncertainty, and automation opportunities when modeling spillways using CFD. So as explained, yeah, my name is Jonathan Bouchard. I'm a senior CFD engineer. I focus on water applications at Flow Science. We are a software company that has been developing CFD simulation software called Flow 3D for over 40 years. My background is in mechanical, industrial engineering, CFD, and other 3D engineering technologies. And it's worth noting that a lot of the material that is in this presentation have been created by my colleagues, Brian Fox and John Wendelbo. So my game plan for this presentation today is first, we'll cover some of the project background. We will explain CFD models, how we set those up and what they look like. Also discuss about the comparison with laboratory measurements. And then we'll discuss accuracy and hardware consideration before my final take-home message. And yes, so by the way, you see this video here on the right. Well, what is this? Looks like real footage or CGI, but it's what modern CFD looks like. Actually, we just have a very high quality and accurate surface representation. So that brings us to the first question. First thing first, what is CFD? Well, CFD, or computational fluid dynamic, is a simulation tool that provides a highly accurate, detailed, and dynamic representation of how the flow interacts with its environment. So in the case of a spillway like this one, you're going to see the detail of the wave runner-up, the super elevation around the bridge piers, and the free surface downstream of the spillway. So this is what CFD does. It's a tool that gives you a very precise and accurate representation of what's happening to your flow. And it's typically used to predict fluid behavior from which we can extract information for analysis or design decision. So let's start with the project background. So the material I will be presenting today was done for a workshop we did back in December 2022. So we had the opportunity to organize this workshop on the topic of CFD modeling for 80 participants from the US Army Corps of Engineers. And we used the Garrison Dam as the backdrop of this study. So we focused on the spillway that we see here on the right, but also on the flood control tunnel, which is an underground tunnel that discharges the flow away from the reservoir and downstream. And that's the example that we used to cover CFD methods. So where is that located? Well, of course, it's in the United States, in North Dakota. So we have an aerial view here. We have the spillway and the flood control tunnel on the other side. And for that spillway, we have gate-controlled OG bays, actually 28 of them that are flowing into that spillway. And if we zoom in, we can see what it looks like in a bit more detail. So these are the two areas of interest for this workshop that we did and the work I will be presenting on. So a little bit of background, there was a technical memorandum including some physical laboratory work that was done back in 1956 with a whole bunch of information and results from their hydraulic lab, including many different models. So 1 to 41 spillway crest model, a 1 to 100 comprehensive spillway, 1 to 25 model of the flood control tunnel, and a 1 to 50 model of the stilling basin and the flood control tunnels. And this report, which is, by the way, available online, have all of these details. And for this work, we focused mainly on the spillway part 4, and part 2, which is the flood control tunnel. So here is what the physical model looks like. On the left, we have the comprehensive model with the reservoir and spillway. Then we have larger model of the sectional spillway model. And here on the lower right, we have the gated flood control tunnel, at least the scaled version, with a reservoir on this side and this radial gate that we see here in more of a close-up view that can open and close to discharge water. So this is what the technical drawings looks like. So we have the different piers of the spillway. This is the profile here of the spillway. There is a radial gate also on the spillway, which controls the flow. Same thing, technical drawings here of that flood control tunnel. So we have water on that side. There's this emergency sliding gate, the radial gate that controls the flow downstream, and there's an air supply tunnel. So this is all of the data we have. So we had access to these rating curves, first for the tunnel. So we add rating curves for different gate openings. So a quarter opening, half open, 3/4, and fully open. Same thing for the spillway. We had rating curves for different gate openings from 3 foot to 15 foot, but also the fully open. We also add water profiles at the center of the spillway gate bay for 2 different pool elevation. So 1,849 foot and 1,859. So a 10-foot difference between these 2 pools. And finally, we had all of these pressure readings along the spillway crest. So they put the piezometer. And so, yeah, as you can see, we had a lot of data to play with. So we took this actual lab data and use it to compare with our CFD models, which are numerical models. So we're comparing the physical world with the numerical world. And so we had access to the CAD model of the spillway with all of the detail. As you can see, it's a pretty large structure. A little bit more of a close-up view here. There are 28 of these bays with gates. And this is what the flood control tunnel looks like. It starts with an 18 by 24 foot rectangular channel that transition into a 22 foot diameter pipe. So below is the detail of the gate, which act as the primary hydraulic control during its opening. But once the gate is completely open, the hydraulic control becomes the pipe itself. So there's a switch going on because the surface of this circular pipe is actually smaller. So it becomes the area of constriction. So when the gate is almost fully open, the pipe transition to being fully pressurized flow and is completely full. So the CAD model based on the report drawing, so we recreated it in the CAD software, including both the emergency gate and the radial gate. So now let's show you or discuss the different CFD models we created. So this is what a CFD model looks like on the right for the gated tunnel system. So what you do is that basically you take the CAD model, you define water elevation, and you basically just push water through the system. So that's kind of how things work. We can see it here. As you can notice, we have the options of defining some objects are moving, like this gate, for example. So we can model the full transient condition in our model. So after the gate opening, we can see that, well, I missed it, but we can see that the pipe becomes fully pressurized. And when the gate closes, we see it depressurized. So we can model these types of behavior. So here's what the CFD model looks like for the spillway. So, okay, you get an idea. So by the way, those have been set up using Flow 3D Hydro. Such models are quite simple to set up and run typically. Typically they run pretty fast. So if you're wondering, like setting up a model like this spillway that we just seen, Takes maybe like 20-30 minutes, and depending on the resolution you want to run, it can take between a few hours to a day maybe. So the workflow in a nutshell, how that works is that you bring in your 3D geometry, which can be a CAD model. It can also be terrain data, bathymetry, or a mix of different types of data. And then we put a mesh around it. So that's our simulation zone. So the size of the mesh cells is what's defining your resolution and accuracy. So we'll discuss that more in depth later. Typically these models, so yeah, we see the meshed version of the CAD. Typically these simulations run on a workstation, I would say 95% of the time. But we have a unified solver, so you can also run these models on a cluster and use up to thousands of cores if you want. And as far as runtime goes, it can take minutes if you do something basic, or a day or multiple days if you're doing something really big and complex. It all depends on the mesh density and the modeling approach that you use. So what are the different modeling approaches? So we'll go through different modeling approaches and how they've been used in that workshop or that project on the Garrison Dam spillway. So because we can attack modeling problems in various different ways. So first of all, like if your flow is kind of homogeneous in the transverse direction, you can just take a slice. So this is a 2D vertical slice using just a single cell in the vertical direction. And this will run very, very quickly. So in a matter of minutes, but it still gives you a lot of valuable information. So not all information, but you do get a lot, and it's very valuable information. So the next step in complexity is to say, okay, like, okay, we have this, I've shown you before, we have this reduced sectional model of the spillway. So let's just model one bay. And also to make things simpler or take a shortcut, since it's symmetrical, we can just model one half and do a symmetry with the other side. So of course, this will not run as fast as a 2D slice, but all of a sudden you start getting some of the head loss and three-dimensionality of the flow for this one bay, like this action here near the pier. And this will now give you very, very good information about how the flow will interact with the piers and the structure. So here's what the model looks like once it's been mirrored. We also applied ray tracing, or like a rendering, to make it look more realistic, but you can plot all different types of variables like velocity, pressures on the fluid. So that's just like a realistic rendering. And yeah, so we did the mirroring, and you now have a full bay and a half, replicating actually what they did with that sectional model in the lab, in fact. So we can really now get the interaction or blockage with those piers. So the next modeling approach, let's say we zoom out and we look at the entire width of the spillway. So here we just see an elevated view, but see in that model, we have all 28 bays. Okay, so you have, so that's something you can do with CFD. Of course, it will take longer to run, so probably a few days, but now you have modeled the entire width, not just a single bay. So I was talking about different ways of presenting the data. Here we see the velocity field. So let's say we went to the general, like, so we took like the full width, but if we take a step back and I look again at this picture, we see the general configuration, and we notice that the approach flow is not uniform. So we have different velocities coming out from different direction. That's because the approach channel is curved. So let's say there will be zone with higher velocity and some zones with lower velocity. And of course, this will affect the discharge both locally and as the whole spillway capacity. So it's something that might be interesting to take into account. So another level of sophistication we can add to this model is to take into account these approach flow conditions using a hybrid approach. What I mean by hybrid is that we can use a 3D mesh block to have full accuracy near the spillway where the flow is dynamic. But then we can use a simplified shallow water model upstream. So the goal of such a 2D shallow water model is to have faster runtime. Because we say it's 2D because it assumes a constant velocity across the depth of the fluid, so it's depth average. So, and for that upstream portion, that assumption is valid because there's little three-dimensionality to the flow. And by the way, these two different mesh blocks are automatically integrated in the software. So with that being said, let's look at how these CFD models compare with the lab results from that 1956 memorandum. So first, let's take a look at our rating curves. So we have rating curves for the flood control tunnels for these different gate openings and upstream reservoir elevation. So for that comparison, we used a 2D vertical slice approach because the flow just happened to be extremely close to two-dimensional in real life. And we actually got some pretty good results, even with the 2D slides. Not perfect, but really good. So you see the CFD results in red and lab measurement in black. And we did the same thing for the spillway with a 2D gate and also got some very good results using that 2D slice approach. Of course, we could do that, and we use that approach for the no peers, because in the lab, they do the test with and without peers. So when you don't have peers, it's good, and you can use that slice. It's a good strategy. And once again, we have very good agreement. And the nice thing with this type of vertical 2D slice is it's running in minutes, and you get very good result. So now if we go to a more complex 3D approach, let's say we have the piers, we can also integrate things like different gate openings. And so we have here the result from a 3D model with all the different gate openings and all different upstream elevations. So as you can see, with all these red dots, these are our CFD models results. So we did a matrix of run, and we overall see a robust and accurate solution across all flow rates. So we also looked at the pressure distribution along the spillway. So we can see where they put or where they had these pressure probes in the lab, and we replicated that with our 3D model on the right. And in this case, there are two sets of results, one with the piers and one without the piers. As you can see, in both cases, Flow 3D Hydro provides just an excellent reading of pressure. So the red line is the pressure along the spillway from our CFD model, and the black dots are measurements from the experiments. So a really good agreement. That was also done with the same pressure measurement with different gate openings. So with a 10-foot and 15-foot gate opening. So different pressure readings, of course, but we can also model these other scenarios with pretty good fidelity. So the same thing was done for free surface elevation. So here we see the comparison with the CFD, which are the colored line, and the black dots are the lab water elevation profiles for the two different pool elevations. So the numerical is pretty close to the physical world there. And finally, if we model the entire thing, let's look at the CFD result. So this is the full discharge that was calculated using that full model. And this other model, this other number, sorry, was actually calculated using the result from a single bay and then multiplying by 28. So all of these bays. So as we can see, the actual full width number is smaller because it considered the actual head loss because of the approach flow condition I discussed about. So we actually measure that capacity loss with that full width model with the upstream model as well. So it came pretty close to the actual lab measurements between 3 to 5%, which is extremely close. So yeah, all in all, what we get from this is that CFD offers you a tool that is accurate, but it also multifaceted. So you can choose between different modeling approach. You can get very quick results using a 2D slice, which is a bit simplified. You can get quick results with a local 3D model like we did for the single bay. But you can also model the full width with all 28 bays and also include the approach flow conditions. So you have all of these different level of sophistication, different modeling approaches that gives you different info with different level of accuracy. But when you choose the right approach and use it properly, you can get very good agreement with the physical lab data, as we've seen. But you know, there are still some potential questions that need to be asked when you do CFD. Is my model any good? So for our workshop, we had the chance to have physical lab data. That's fantastic, but sometimes you don't have access to that data. So question is like, oh, sorry, how wrong is my model? You know, when we do training, we always say that any CFD model is wrong. The question is it wrong by 1%, by 10%, or is it wrong by 100%? And so is it quantifiably wrong? How can I use this result? What's the cost, computationally speaking? So these are all good questions that everybody should be asking when looking or thinking about CFD model. So for the Garrison Dam workshop, we did a lot of sensitivity analysis. So we took some of the discharge and we looked at the difference between the results we got and the lab measurements. So you have the percentage of difference between the CFD and the lab measurement. And we did different runs with different resolution. So this top point cloud is with the coarse mesh, 2.2 feet cells. We have the intermediate mesh, a finer mesh with 1.1 foot cell, and finally a fine mesh with 0.6 foot cell. So we see that with the coarse mesh, the overall envelope is within 10 to 15%, which is already great, by the way. But okay, if we refine the mesh and we use a finer mesh, then it goes, all this entire cloud goes down to 4 to 8%. So we improve our accuracy by going finer. And finally, if we use an extremely fine mesh, we get between 1 and 4%, which is practically within experimental accuracy. So what's the conclusion? The conclusion is that when you refine the mesh, your result become more and more accurate. And that's what we saw here. So yeah, so this is, like, in summary, this is really important. Accuracy improves when you refine your mesh. So this is the #1 driver of accuracy. And you can plot it in various ways. So this is for the flood tunnel. We have the lab data in gray. And then the red is the coarse model, the yellow is the medium, and the blue is the fine. And you see that in every cases, as you refine the mesh, you're getting closer to the truth. So the meshing does move the CFD solution consistently toward the lab data. And accuracy consistently improve as you refine the mesh. So that's the moral of the story here. So we did kind of the same type of analysis. This is a mesh conversion study for the flood control tunnel. So by increasing the number of cells, so by going with smaller cells across the opening of the gate, you can see that as you refine your mesh, you go from 11% up to down to like 1 or 2%, which is pretty good. But of course, when you reduce your mesh size, the total number of cells in your simulation will increase. So that will affect processing time. So that brings me to my last topic, runtime. So let's say we have a model like the one we see on the right, which might take maybe 24 hours to run on a 10-core computer. If we run it on 40 cores, it goes down to 8-9 hours. Then if you put it on a cluster, it might only take an hour. So once again, here, there's no secret. The more cores you have on your processing machine, the faster things run. And we did a bunch of benchmark with different types of architecture, different chips, Intel, AMD, and also different types of architecture of what's available in the market in terms of cluster, AWS, Azure, and others. And we kind of see the trend here. So it's the runtime for CPU cores. So of course, there are some discrepancy. Some hardware almost like for the same number of core might run like twice as fast as another one. But the general trend, as you see, is that the more core you have, the faster the runtime. And yeah, one final thing is that the other dimension of modern CFD is automation. So when dealing with such a large number of simulation, like the one we did for this workshop, we don't want to do it any of this work by hand. So we can fully automate all of these simulation. So we specify what mesh size we want to use, what gate rotation, what water elevation in the pool. And then we push that, and we all the simulations are automated. So you get the flow rates. So you have your inputs. You run your simulation with all of these different inputs. You can automatically extract data and post-process the results and perform any calculation you need. So final take-home messages. First of all, what we wanted to do with the U.S. Army Corps of Engineers was to demonstrate ease of use. Of course, okay, we didn't do any simulation today, so that was just a condensed version. But as a software company, we really focused on making the model setup really simple. There's a rapid learning curve. Meshing is really simple and fast, and leveraging computer resource to have fast runtime. But in my presentation, I wanted to give you also an overview of the different modeling approaches using slices, vertical slice, 2D, 3D model, hybrid approach that gives you different type of info and can be really accurate. All of these things are robustly quantifiable. So let's say as a modeler, when you do and you've done mesh study, you basically know ahead of time, okay, if I use this mesh resolution for this type of structure, I can expect this type of accuracy. And finally, all of this is very well integrated with automation and high performance computing. So you can be really efficient doing these types of analysis like the one we did, or all these simulations we did for the workshops. And yeah, so CFD is becoming more and more mainstream. It can be used now over a wide variety of water-related projects. And it's a great tool for engineering and productivity. So yeah, on that, I thank you for your attention, and yeah, I'll be glad to answer any questions. And if you want to reach out to me, feel free to reach out on LinkedIn and by email. And just by the way, I'm just putting this little video. It was done for the Isabella Dam. It's once again data that was provided by the U.S. Army Corps of Engineers. So we're showing flow velocity over terrain data with the satellite map. And then this is ray tracing. So this was done more of a post-processing exercise. So thank you very much.
Thank you, Jonathan, for a very interesting presentation. Yes, Q&A session is coming very soon. Before that, just a short presentation. Can I ask you to stop sharing the screen? Thank you. And now I will share my screen. So just a short final presentation from my side. So again, hello to everyone. Nice to see you here in a large number. I will briefly talk about the ICOLD Young Professionals Forum. And I will start by explaining, because I guess some of you have never heard of us, what does this even mean? So ICOLD Young Professionals Forum is a body within ICOLD, and our mission is to aim and to target young professionals in the field of dams and in a very broad field, not just structural engineers, but all professionals in the branch in the beginning of the career. And by definition, young professionals in ICOLD are the professionals that are younger than 40 years. So our goal is to encourage young professionals and to provide mentor opportunities, provide opportunities for knowledge transfer, and provide opportunities to network and to share experience. So for example, this webinar today is one of those examples of our actions. Moreover, we also want to inspire young professionals to become active within ICOLD and within the national committees that are included in the ICOLD. By the way, ICOLD has more than 100 member countries. And then furthermore, we try to encourage the young professionals that also within their national committees that they form their own young professional networks and start being involved also in the work of the technical committee. In the beginning as the observers and then more and more. Because if not else, technical committees are also a very good place to gain new knowledge, to grow connections. So the story of the young professionals started in 2009 and we were activated in the year 2011 with the first inaugural meeting. Since then, we meet in person at least once a year at the ICOLD annual conferences, and in between we remain active on regional events and also we remain active online. And at this moment, I would also like to acknowledge the past chairs. Let's say we are now the 5th generations and the 4 chairs before me are the ones who paved the way for us to continue. The board of ICOLD Young Professionals consists of 6 members and 1 chair. All of the positions are voted and our term of office is typically 3 years. We aim to be representative and diverse. We want to have a member of the board who is also a member of the National Committee who is organizing the next ICOLD meeting so we can be involved in the program of the next ICOLD conference. And we also have we have full trust in the nominations of the National Committee. So if you want to become a member of the board, the elections are every year. For example, this year in New Delhi during our official meeting, there will be 2 positions open. And to become a candidate at the elections, you need the support of your national committee or your national committee has to nominate you. And then you have to be present during the meeting where you have an opportunity for an elevator pitch to present yourself. Then all the young professionals attending the meeting have a right to vote. And the two members on the elections that will have the most votes will be the one that will be elected to work with our board for the next 3 years. And yeah, the call will be announced 2 months before the meeting in New Delhi. The meeting in New Delhi is in September, so you can expect the call to be announced online in the middle of the summer. Now, we also serve as an umbrella for the national YPF. We provide support. So far, 33 ICOLD countries have established their own national branches. Since there are more than 100 ICOLD member countries, we still have room for improvement. So if you don't see your country here, mark with an orange color. If you want to change this, activate yourself. If you need the support, contact us and we will help you in any way we can. The activities that I'm talking about, the week when the conference of ICOLD happens is very active. We have our own meeting, we organize our own social event, we have mentorship roundtables, and we organize keynote presentations by the distinguished dam engineers. Moreover, young professionals have a reduced fee to attend the conference. Also, if you send a paper and you have a presentation at the conference or you have a poster at the conference, there is a competition for the best poster and paper award happening at every conference. In between these yearly events, we stay active online. We organize webinars, we organize online meetings, and we also support a LinkedIn group, which has over 1,000 members, where we post anything that we believe is interesting for the young professionals in the field. Now, the group is closed. You have to enroll in it, but once you're a member, you can also share there. So it's sort of a interactive platform. So if you're not included, yes, we recommend you to click and to get included. Also, we have a YouTube channel where we post the webinars. All of the webinars are recorded, also this one today, and the recordings are available on the YouTube channel, so you can watch them later on. So I will conclude with this. This is a very short presentation. Here you have some QR codes so you can access the web pages that I mentioned. And now is the time to continue with the Q&A session. So we had today 4 presentations and 5 presenters. If you want to ask a question, raise your hand and moderator will unmute you and give you the opportunity. In between, there are some questions in the chat. So to get us started, I will read the first question of in the chat, and in between, become courageous and ask more questions. And the first question was to Narjes. Somebody is curious if the iData tool is freely available.
Is that we prepared the data for analysis for this 3 job that I mentioned is ready and it's doing great, but we are not going to release it yet because we are a bit perfectionist. We want to make it perfect and we want to add lots of other options to it. So we have some ideas how we can make it better and better. So every time we're happy with the enough options it has, we can decide about how to release it.
Okay, thank you. We are looking forward then to see it live. The next question is to Stefan. Which is the platform and in which you collected all the information coming from the site, and how do you link this to the BIM model?
Okay, thank you for the question. It's a key question for these kind of solutions. The solution that I've shown is based on a SharePoint application, and then we linked it with different software solutions. And this I don't want to make publicity for different companies, but actually there are solutions that already incorporated certain interfaces in order to connect it with a centralized database.
Okay, thank you. The next one is to Jonathan. So your workshop extensively covered the setup, execution, and validation of the CFD models, focusing primarily on hydraulic structures like Garrison and SPILLWAY. However, it did not address the influence of environmental variables such as temperature, sediment transport. Could you maybe discuss how these factors might impact the CFD results, and if there would be any additional modeling techniques or adjustments needed to adopt?
Yeah, thanks. That's a very interesting question. Indeed, yeah, it was just an overview of one specific project, but you can adapt your CFD model, let's say, well, first of all, for like different temperature, you would change you specify your water density and properties. And by the way, there was also another question talking about fluids that I answered in the chat. It's also possible to model non-Newtonian fluids like tailings dams. It's something we can model with the Herschel-Boxley model to define rheology. But yeah, going back to this question, it's yeah, so you start by doing a hydraulic simulation. This one was just purely hydraulic, but to model like real life phenomenon, you can add additional physics. So you can model, you mentioned in your question, sediment transport. It's something we can model. You can add, let's say, surface roughness. Let's say you have grass or growth of stuff on the spillway. So that's something you can also define in your model. You can add things like air entrainment. Let's say you want to model bulking or like air being entrained in the flow, so expanding. So yeah, the idea is usually to start with simple, with hydraulic simulation first, and then Flow 3D Hydro, you can activate like different physics model to model some more complex phenomena.
Okay, thank you. But I also saw that you already replied the question regarding comparison with the measurements in the laboratory. Can you maybe also comment to those of you who didn't read your question?
Yeah, there was a question about what challenges do we have modeling or like comparing with the Garrison Dam case study. In this case, well, I would say, first of all, dams and spillway is the oldest application for a CFD in civil engineering. So like there's maybe like 40 years of usage or like 30 years of usage. So upfront, like it's something that the software is already preset for. And the main challenge for this analysis was just the sheer number of simulations we had to run for all these different structures, all these different conditions. So using an automation tool was great for that. And also the nice thing is that you can either model at the scaled down version, but you can also model the one-to-one model, like in the real life dimension, which is not possible in the lab. So yeah, that's one nice thing that you can, when you use a numerical lab instead of a physical lab, that you get.
Okay, thank you. And now a question for Étore. Now it's in Spanish, so I will do my best. But basically the question is, if maybe you can tell first, how many instruments do you have at Itaipu and how often do you take measurements and something about data management from these instruments?
Yeah, I read this questions in Spanish, so I could understand. Yeah, how often do the instrument measurements take place? The readings occur weekly, fortnightly, monthly, quarterly, and semi-annually. And the second question is, in the case of topography, what closing precisions do you use for planimetry and altimetry? The closing precisions are 5 millimeters for planimetry, and for altimetry is of first order with a tolerance of 0.5 times the root of K in millimeters. K is the length of the dam. In our case is about 8 kilometers. May I continue with the other one?
Yes, do continue.
Okay. The other is, do you have data on the loss of efficiency of the drains and or their recovery after cleaning? Are they effective? The answer is yes. We have data on the depth of measurements of all drains before and after washing, and we are creating an index to create a priority ranking of the analysis, so we could focus on the worst one.
Okay.
And the last one I received is what is the method used to clean foundation drains? The answer is we use water from the lake or water supply points available along the dam to move dirt from the bottom of the drains. We take care to prevent the pressure from being so high that it could damage the drains. So that's the main procedure we use.
Okay, thank you. Maybe I will just add one question. How many people do you have involved in the maintenance of the dam? Precisely.
We have a company. We contract the external company to make this maintenance, and they have almost 15-20 people working in cleaning, making maintenance in these instruments.
Okay, thank you for now. Now a question for Narjes. Regarding the highest frequency, which frequency should be used to define the mesh for the numerical model?
The frequency of the record of the earthquake that we are adding to our model, the highest one that we are applying.
Okay, thank you. And while I have you here, I will also ask you another thing. So if you maybe can comment, so sometimes in the numerical model, when we apply dynamic load at the bottom of the model, we can read the stress at the same element, but the read is not the same as we applied. Can you maybe comment on this?
I think sometimes, yes, that happens, and that comes from the numerical error, and that is that when you limit the foundation of a real foundation that is infinite foundation, and you make limited into a specific depth, that because you don't have a magic computer to calculate the infinite elements. So when you make a model just a specific depth of the foundation, if this depth is not enough large, so when you apply the dynamic load bottom of the foundation, these waves may comes up and again come back to the foundation. That shouldn't happen. So the thing that you are reading is not just the one that you are applying, but also the wave that came back again to that element, and that makes the problem.
Thank you. And the next question will be, to date, do we have any practical application of the CFD on dam breach analysis for tailing dams? So for John.
Yeah, that's a very good question. I presented last fall at the Canadian Dam Association conference some work on tailings dam failures. The challenge with tailings dams is to properly, with tailings and non-Newtonian fluid, is to properly define the rheological parameters of this type of material. But if you are interested, just send me an email and I'll send you a link to this presentation. So basically, we compared a numerical CFD model with actual physical experimental results from the USBR. They have this debris flow flume, so they do a mix of gravel and mud, and they just open the gate. And so we compared, we did the same setup, but numerically. So it was pretty interesting for that.
Okay, thank you. There are more questions for you. Does Flow 3D Hydro allow bidirectional interaction with deformable structure?
Yeah, that's a good question. So we do two-way coupling or bidimensional interactions with floating objects or moving objects. Deformable structures are a little bit more challenging because we need, and there was like another question related to can we model like deforming structures or like how a wall will move due to hydraulic. So we don't do finite element analysis. We can provide information on forces and pressures on object. We can have floating objects or moving objects moving with that. But in the case of a rubber, I think it's a bit more advanced, but you can basically define a very high density viscous fluid as your rubber and model these types of interaction this way. But generally speaking, we don't do finite element analysis, at least in Flow 3D, so it needs to use other models to do that.
Okay, thank you. Now, a question to Rubén Sancho. How can one quantify or estimate the movement, both horizontal and settlement, of a dam wall using drone survey georeference photographs?
We can estimate with different methods. It depends on our structure. For example, if we have a very good point cloud, we can compare both point clouds. Or if we want to make the comparison since a model, we can compare model to model, model to cloud. It depends on our structure. And then we have several algorithms, and it depends, or we have a flat surface or with very different angles. It's better one algorithm or another. And we have a point cloud. It's all points are your reference, and all points have their coordinates. Then the algorithms check the coordinates of one point in the first data collection and in the second data collection. And then we can, our result is the difference between these coordinates.
Okay. Do you maybe have any experience with, let's say, INSAR data? Ruben?
Can you repeat, please?
If you have any experience with INSAR in post-processing INSAR data, for example?
No, with only point cloud with terrestrial and drones.
Okay.
No, with INSAR.
Thank you. A next question for Narjes. Can you suggest a freeware software for the convolution of time history acceleration input according to foundation configuration?
Let me think. I'm not the representative of any company here, but the Berkeley University, they have lots of different codes for doing different things, and normally they put them available, accessible for open access. So if you search there, probably you can find them. And also some software gives you like a 1 month trial free. I think the thing that I remember, I'm not sure. I think that Soils, I think, has 1 month free trial that you can check, because I don't have updated information about that.
Okay, thank you. And can you comment on how you treat the hydrodynamic influence? So reservoir dam interaction. Do you use fluid elements, interface elements?
I lost you.
Okay, I will repeat my question. I'm sorry. How do you treat hydrodynamic?
No, I lost my window here.
You want to share with us something?
No, just okay. Now I have you again. Sorry. Can you explain again?
How do you treat hydrodynamic influence with the reservoir dam foundation? Do you use fluid elements or interface elements?
It's quite depends on the computational cost that you want to accept, and also the software you are using, and also how important is that part for you. So sometimes you just can simulate it with the added mass of Westergaards simply, or sometimes you can just simulate some simple elements, and you add the far conditions and near condition and contact condition. That's like the thing that you can do in Abacus, I think. And yeah, any element that you can, that they have the degree of freedom of pressure, because I think that is important for the simulation of the hydrodynamic of the water, is simulating that pressure. So every element in the manual, the software you are using, check it which elements support they have the degree of freedom of the pressure, and use that element.
Thank you. Yeah, that's a lot dependent on which software we are using.
Yes, yes.
Yeah, thank you. Question to Stefan. How long would it take to implement an AD system on a dam? Months, years?
Good question. It depends on the level of detail. I think in 1 year you can get quite far, but don't do everything at once. Maybe you should choose some use cases, some processes you want to implement, and there you can start. I think you can have something going on already in a year. And then I think the implementation is also important, because it's not just installing a program on your computer. You have to consider all the people that are working in your company that have to use it. Because if everybody has to work from one day to the other, all working processes, this will probably fail, because maybe they are not willing to it, because it's also a lot of work. So do it progressively, and maybe just with the first milestone of 1 year to see what can you achieve, which is reasonable, and then go on. I think a whole process for a very complete integrations takes more than a year. But I think in a year or a bit less, you can start very well with it.
Okay. I mean, I guess it also depends on how big the group you have and what are your motivations, right?
Yes, yes.
And
Also the age, maybe. The willingness to use new technologies, yes.
okay, yeah. Another question to you or to Ruben. What are the key considerations where researching and implementing a new digitalization management system for the dam safety management? And additionally, if you could provide any advice on integrating this new practice into existing operations.
Was not, you mean a management system to incorporate it?
Yeah, I'm also not sure what the question exactly means, but
I think it goes a bit like in the direction I've already answered.
Yeah.
I guess so.
Yeah. So do you have any additional advice to it?
Incorporate the people that have to use it. Maybe not start with, let's say, incorporate your software team and also the engineers. But don't let everything do the engineers, but not everything do the IT team. So I think this is quite good to have a collaboration in the beginning. And then when you implement it, maybe with a project, just look for people that are willing to do it. And then they also transmit this motivation and to the people that maybe are, for them, it's more difficult to implement new procedures.
Okay, thank you. Maybe I will add something, and it's a little bit open. Maybe also somebody else can say something. But a lot of the attendees that listen to your presentations are young professionals. So can you maybe say some words? Are there opportunities for the young professionals in the field? Are there jobs available? Do you have anything to say about that? Nobody wants to answer, right?
Yeah, it's a general question for everyone. No way, but I can say, like, on my end, that like computational fluid dynamic is a growing field. It's part now of a lot of academic curriculum. As a matter of fact, for those students or young professional, if you're still related to a university, we offer free licenses for academics. And yeah, it's the learning curve is not really steep when you have 3D software experience and a background in water. So I think it's a nice skill that you can add to your resume if you're interested, of course.
Yes, I also want Mateja to encourage people to form part of the Young Professionals Forum. I think that on dam engineering, we are living a very good time because dams are going to be critical in energy transition and in the fight against climate change. So for young engineers to be introduced in this career and this profession by the Young Professional Forum is a very good way. So I encourage them to do it.
Thank you. Thank you. Yeah, there are plenty of opportunities. I think we are lacking people, not opportunities right now. Okay, another question to John. The CFD model you have shown fits perfectly with lab, but do you trust CFD model without having a physical model to compare?
Yeah, that was a pretty good question. So for certain application, I would say yes. Everything, if it's just hydraulic or water structure interactions, we know from experience that it's like we get very good accuracy. There's been a lot of benchmarking and validation done through the years, like especially for dams and spillways. However, for other, so like as you've seen in my presentation, for these type of application, we can be pretty confident with the decent resolution model to achieve less than 5% accuracy. But for other application, let's say sediment transport or air entrainment, validation, like the model, the uncertainty can quickly go like maybe 20–30%. So in this case, validations, like when you use advanced physics, validation is required. I mentioned that on our website, we have the Flow 3D Hydro website, we have a section with the technical papers. So you can find a lot of validation or existing work that have been done on different types of applications. So it's all listed by different type of application, and like people using researchers or people using the academic program. Sometimes they publish paper, they did validation. So it's a good inspiration or it's a good source of information if you're considering CFD for an application that goes like a little bit away from the beaten path. So I invite you to take a look.
Thank you. When I was studying, one of my professors said that all of the models lie, including physical, and basically it is important to know the benefits of the model that we are using, and as engineers know what we are doing. It's not just blindly to believe, but we have to do a good job.
Yeah, you're right. Yeah, model is always wrong. It's just how wrong is it? 1%, 100%. Yeah.
Yeah, okay. The next question for Narjes. Can you suggest an open source software for frequency matching and scaling of time history inputs according to the target response spectra?
Yes, the online website up here that I mentioned in the presentation also, it has a part that you can upload your target. You can upload your design response spectrum, and again, according to that one, you can do the scaling. Yes.
Can you maybe copy the link to the website in the chat?
Yes, yes, yes.
Thank you. And now there is another question, but I'm not sure for whom is it intended. But basically the question is if, well, the author of the question is questioning what are the solutions for mitigate the filling of reservoir with the sediment. Now, is it dredging or any other raising the dam? But I'm not sure who to ask to answer this. So if is any of the panelists volunteering to share some words on the topic? Yeah. Well, definitely reservoir sedimentation is a challenge that we are all facing now, and probably the same solutions cannot apply everywhere, but we have a challenge ahead to sort this out, but maybe not this webinar is not the proper panel to ask this question.
If the question is about quantify the sediments, I don't know if that's the question.
No.
And then,
yeah. Otherwise, I think we answered all of the questions. Does anyone want to ask anything? Do it quickly now. Okay, then I will say thank you to all of the presenters. Your presentations were very insightful. And now I would like to ask Alfredo Granados Garcia, the Vice Chair of European Club of ICOLD, to close this session for today.
Oh. Thank you, Mateja. First, I would like to thank the co-organizers, SPANCOLD and ICOLD YPF, and also the speakers for addressing these important topics. We had excellent presentations and case studies from which I think we can learn a lot. And I would also like to thank all the participants. I have been following and over 280 people, and for the attendance and also for the contributions to have a fruitful questions and answer section. And well, also I would like to tell that as a SPANCOLD president, Carlos Granell mentioned, this webinar is part of the European DAM Day, and this initiative by the ICOLD European Club, following a proposal by ICOLD, aims to communicate the benefits of dams. The European Dam Day will be namely celebrated tomorrow, the 29th of May. And so please check our LinkedIn profile for information that will be launched. And we will be using hashtags Dam Day and Dam Day Europe. And we would appreciate your participation and help for disseminating the news. And finally, on behalf of SPANCOLD, I would like to announce the Madrid candidacy to host the 29th ICOLD Congress in 2028. And following this excellent organization of the webinar, I hope this to become a reality. And thank you very much, and to all of you, have a nice day. Thank you.
Thank you. So with this, we are concluding this session. Thank you to the speakers and to the presenters. Thank you to the presenters and attendants. Yeah.
Thank you, Mateja, for organizing this.
It was a pleasure. Goodbye.
Thank you very much.
thank you.
Thank you very
Bye-bye.
much.
Thank you.
Bye-bye. Thank you very much.
Thank you very much, everybody.